Hello friends, today we will be discussing transition curve and particularly spiral transition curve. As you know, there are several forms of transition curve. It can be Bernoulli curve also, Leibniz curve also, but the most popular is the spiral curve. And the basic property of a spiral curve is that the radius reduces proportionate to the length. And that is the curve which satisfies almost all conditions of an ideal transition. So at any length L, if the radius is R, then R into L is constant. That is the property or the equation of a transition. And if the length of transition is, let us say, Ls, at the end of transition there will be a circular curve. So let us say the radius of circular curve, then this will be equal to LR equal to constant. This is the governing equation for a transition, a spiral transition curve. Now here is a circular curve in the center and a transition is provided from this point to this point. Now this transition is spiral and from here to the tangent point again. So you are introducing a circular curve between the tangent, that is the circular curve, and the transition is basically connects the tangent point to the circular curve. Now, this is TP. That is the tangent point from where transition starts. That is the tangent point where the transition ends on the other side of the curve. And this is the point of intersection where these two tangents meet. That is the length of tangent. Now, this distance by which this circular curve is moved inward just to accommodate this transition, that is called the shift S, and this is generally taken at a distance of k. Now k roughly is half of the length of transition, but I will tell you it is different from Ls. Ls is the length of transition. Now, this is a deflection angle. Deflection angle is generally known in the field, and that is the length of circular curve, LC, and that is the deflection angle of the circular curve, and these are two deflection angles of transitions, theta S and delta C. Sum of all these is delta. This is delta. The deflection angle at any length, in the case of spiral transition, the deflection angle at any length is such that d theta upon dl is 1 upon r. That is, you can say, the governing equation for a transition, a spiral transition. And I told you Ls into Rc is equal to L into R. So 1 upon R can be written as Ls into Rc. Or you can say that d theta is L into dl upon Ls into Rc. Integrate this equation and put the boundary condition, then you get theta is equal to L square upon 2Rc into Ls. This is equation number 2. That was equation number 1. At the end of the transition, when L is equal to Ls, theta becomes theta S. And therefore, this theta S will be Ls square upon 2Rc into Ls, or theta S is Ls upon 2Rc. When you take theta in radian, when you take theta in degrees, then it is 28.65 into Ls upon R. That is the total deflection angle of a transition. It will depend upon the radius of the circular curve and length of transition. You can say equation number 3. For the purpose of setting this curve, This is the transition and you have a circular curve here. So offset y is taken at, let us say, distance x. X is along the tangent, whereas L is along the transition. And this is, I told you, this is the shift S, which is taken at a distance k from the tangent point, and this offset at any x distance or L distance is dy upon dl is given by sine theta. That is how in the case of, because the radius changes with the length and therefore deflection angle will change with length. X is taken along the tangent and L is taken along the curve. In field also we generally take the L, length of the, along the length of the curve. Now from this equation, if you put value of dl in that equation and you expand sine theta series, then you can get the value of y. That is a bit longer procedure. So you get dy is equal to ls into rc upon l into sine theta into d theta. And you know the sine theta series is theta minus theta cube upon factorial 3 plus theta 5 upon factorial 5 minus theta 7 upon factorial 7 and so on up to infinity. So this is to be integrated now. So you can find out y. So y value will be L cube upon 3 into 2 ls into rc minus L power 7 into 7 multiplied by factorial 3 into 2 rc into ls whole cube plus L9 and so on, all these terms. Now if you neglect all these terms and take only y as a first term, then it is L cube upon 6 rc into ls, and that is the equation which generally you get in the textbook, that the offset is at any length L or x is given by this equation. But actually y is less than this value because they have a negative term here, then you have a positive term here, a negative term here. So it is slightly less than the actual value. And therefore to compute value of y accurately, there is a table given in IRC 38 for computation of y in terms of L. I'll tell you about this table a little later. Another important parameter in setting of the curve is the tangent length, Ts. Now Ts is given by this equation, k plus rc plus s into 10 delta by 2. Now this is delta by 2. This is delta by 2. This is k, which is measured along x, where you get the shift s. This is k. This is shift s, and that is the rc. So this ts will be k plus remaining rc plus s. You rc plus s physically you are moving here, and then tan of delta by 2, that is, now k, as I told you, it is approximately ls by 2, and that is how you measure the shift. Shift is taken at half of the transition length. But actual value of k is given by this equation. K is x minus r sine theta. You can just see in this figure that it is x is taken along the tangent again. And again, if you expand this sine theta series, then this k will be half of ls into 1 minus theta square upon 5 into factorial 3 plus theta 4 upon factorial 9 into factorial 5 minus and so on. So again, if you neglect all these terms, you get half of the transition length. But actual value is less than half of the transition length. And therefore again, the table, if you enter table given in the IRC 38, you will get the value of k in terms of L. And similarly, this EC also you can find out. That is the maximum apex distance, EC or ES, that is RC plus shift into sec delta by 2 minus RC. And the shift is given by this equation, y minus RC over sine theta. All these equations you can write mathematically using this figure. Now y is the offset at k and RC radius circular curve. Versine 1 minus sine theta is called the versine. So again, if you expand this series, you get S is equal to half ls into theta upon 3 into factorial 2 minus theta cube upon 7 into factorial 4 plus theta 5 upon 11 into factorial 6 and so on. The first term ls into theta upon 6, half ls into theta upon 6. Put value of theta. Theta we have calculated, okay? Theta. So you get approximately S is L square upon 24 RC. This is what you get in textbook. At shift of circular curve is L square upon 24 R. L is the length of the transition. But again, it is less than this value because you have these terms also. So again, S is calculated or estimated from the tabular values. So that is how we design a spiral transition. So the example is taken from IRC 38, that design speed is 25 km per hour. Deflection angle is 165 degree. Minimum radius of the curve is 20 meter. Width of roadway at hairpin band means after extra widening is 7.5 meter. Width of normal road before transition, where the transition starts, is 4.75 meter, and minimum length of transition is also specified as 35 meter. And design a fully transitional curve. So let us say you have this type of curve. It is fully transitional. This is now 165 degree. So if you take half of it, it is 82.5 degree. And that is your tangents here, and you have some sort of shift also here. S. And this is inner curve. So you have now three curves. One is the inner curve, middle curve and outer curve. Center line of the rod, inner edge, outer edge. So let us first take the inner curve. In the case of inner curve, the radius is RC is 20 meter. That is minimum radius. Theta is half of delta, that is 82.5 degree. You remember this equation, theta s is equal to 28.65 into Ls upon Rc. Now theta is known, Rc is 20, you can find out what is Ls, length of transition. So this length of transition is now 57.59 meter. Now what it says, the minimum length of transition should be 35 meters and this value is 57.59 meter and therefore it is okay. Now this length of transition you can find using the table also. So if you enter the table corresponding to a theta value 82 degree and 83 degree, here you get the value of R in terms of L. So you interpolate the value between 82 and 83. So corresponding to 82.5, you get R is equal to 0.3473 Ls. This you get from the table. And because R is known 20 meter, so you can calculate Ls 20 upon 0.3473, 57.59. So that is how that table is to be used. Now once you know this length of transition, the next is to find out the shift. For shift, again go to table, because if you calculate shift using equation L square upon 24 R, this will not be the correct value in case of transitional curve, and therefore you again go to the table for again theta is equal to 82.5 degree and you get this value as 0.1115 Ls. Because corresponding to 82 degree you have 0.1109 and for 83 degree it is 0.1121. So the mean of these will be 0.1115. Ls is now known and therefore S will be 6.42 meter, because Ls is 57.59. Ls is 57.59 meter, so that is the shift, 6.42. If you calculate using this equation, it will be 57.59 upon 24 into 20. This will be 6.909. So that is the difference between approximation and actual value, 0.5 meter. Similarly, you can now find out what is ES, that is the apex distance, that is RC plus S into sec of delta by 2 minus RC. You know all, RC is 20, S is 6.42, delta is 82.5. So you can calculate this value, that is 182.41 meter. And again, you can also calculate this tangent length, TS. I told you it is given by this equation, K plus RC plus S into 10 delta by 2. Now here K is not known. K is not half of the transition length. It is less than that. So again for K value, you go to the table corresponding to 82.5 degree curve or 82.5 degree deflection angle. You find out what is K. K is 0.4675 into Ls. Ls is known, 57.59. So this K value will be now 26.91. 26.91. RC is 20, S is 6.42, delta 82.5, and therefore TS will be 227.58 meter. If you want to find out the Y value, that is offset, Y is also given in terms of L in the same table. So you can find out at different L values what would be the offset. So that is how you can set the inner curve. Now the middle curve, if you set the middle curve, now in the case of middle curve, the radius, this R will be 20 plus half of the total width here, that is 7.5 meter by 2. So it is 23.75 meter. Now how do we calculate shift now? You have a inner curve and you have a middle curve. And this is the tangent of the outer curve, middle curve, and that is the tangent of the inner curve. This distance is 4.75 by 2, middle curve. That is the width of the road here. And let us say this is the shift of the inner curve and that is the shift of the outer curve. That is the shift. So let us say this is SI, I for inner, and that is SM, M for middle, and this is the RI, and that is shift, the shift of the outer curve, middle curve, and that is the radius of the middle curve. So RI plus SI will take you to this tangent. So RI plus SI plus half of the width here, 4.75 by 2, that takes you to this tangent. And if you subtract this outer radius, middle radius here, you get this shift. So minus R middle, that is the shift of the middle curve. That is how you can calculate. So this shift is now 20 plus 6.42 minus RM. RM is, we calculated 23.75 meter. So this is now 5.46 meter. Now you know S, that is shift, and you know the radius. So you can find out what is S by R. SM, I am putting M for middle curve, and RM is now 5.046 divided by 23.75. This is now 0.2125. Now enter the table with this value of S by R and find out what will be the theta value. Reverse process. So corresponding to this, if you enter the table for S by R equal to 0.2125, you get a theta by interpolation is 66.2521 degree. And once you know theta, you can find out length of transition, LS. You know theta is 28.65 into LS upon R. So theta is 66.2521, R is 23.75. You can calculate the length of transition. So length is now 54.91 meter. Once you know the length of transition, radius, you can again enter the table, find out value of K and find out what is TS. You can also find the offset Y by again entering the table with S by R equal to 0.2125 or with the value of theta 66.2521. Once you know all these parameters, now similarly you can draw the outer curve also. Now for outer curve, this radius will be now 20 plus 7.5, 27.5 meter. That is the radius of outer curve. So in the same manner, that is your circular curve, and this is the shift of this. You can find out what is shift. So shift for outer curve is, that is inner curve plus shift of inner curve plus 4.75. Now instead of 4.75 by 2, if you take the total width of the road, you reach to this tangent, and then subtract the radius of the outer curve minus RO. So this is 20, this is the new S 6.42 inner curve plus 4.75 minus 27.5 meter. So S for the outer curve is 3.671 meter. Follow same step now. Same step. You follow same step. Now you know S, you know R. Find out S upon R. And with S upon R, enter the table. Find out value of theta, appropriate value of theta. From theta, find out value of LS, transition length. When you know the L, you can find out X, you can find out Y. You can find out K also. So all parameters of transition are now known. That is how you can design a transitional hairpin band. Thank you very much for watching this video. If you have any question, you can write.